This lecture is about applications of the normal distribution, and whereas we've talked about calculating with the standard normal before, one that has a standard deviation of 1 and a mean of 0, here we will be talking about one that has a general, just will be able to calculate with any mean and any standard deviation. So if let's begin here. If we have if x is a random variable and it has a mean mu and a standard deviation sigma, and you take its z-score, and that's the standard normal random variable, then we say that x is a normal random variable with mean mu and standard deviation sigma. Okay, so we have a special notation for it. That means we're going to be writing stuff down like this a lot. Okay, and so this, I'll go back to my real data that I had from the program I administer. Here we've looked before and we've seen that it's a nice fit for the normal curve. It has a mean of 108.7. It has a standard deviation 32.5, and there are 163 pieces of data here, a population of 163. Okay, again, here is the graph where we juxtapose the normal with the actual data. It's nice, but it's not perfect. But can this still be useful? Okay, an application. So let's x be the random variable from our real data. Then x is normally distributed with a standard deviation a mean 108.7 and a standard deviation of 32.5. We want to estimate the number of data items such that x is greater than 124. 124 was chosen simply because everybody on campus has to have 124 hours before they graduate, and graduating is what this program is about. So what is the probability then that x is greater than 124? Well, in order to do a normal calculation, what we do is I massage this data so that it is in standard form. I take the z-score of this event. Okay, so I subtract the mean and I divide that difference by the standard deviation. So this 124 comes from here. This 108.7 comes from the fact we've established my data has a mean of 108.7, and we divide it by 32.5 because we have established that I have a standard deviation of 32.5. I do the math and I round this off to 2 decimal places. Okay, on this sort of calculation I'll always round off to 2 decimal places because I'm going to be looking this up on a normal table, and my normal table only goes to 2 decimal places. So this is the probability z is greater than 0.47. So x greater than 124 through my taking of the z-score translates to z greater than 0.47. In terms of an event, it's this tail right here, the probability of this tail. Now remember, we calculate tails. We'll have a 0.5, and this is a thin tail. If it were to start out here and go this way, it would be fat, okay, but it doesn't have 0 in it, so it's a thin tail. I subtract the table lookup for 0.47, right? I go to my normal table, over here, I do my lookup 0.47, and that gives me the number 0.1808, and I do the math, and it turns out 0.3192, which is 31.92%, or 31.9%, or about 32%, right? Okay, now that this proportion of our data then should be above 124. This number of our population should be above 24. Well, our population had 163 people in it, so I take this proportion times 163, or this proportion of 163, I get 52.0. Then I go in by hand, okay, and I do a count of the data. I actually have my data set here, and I do it, and it turns out to be 51, which is nice. It's not exact, but it's nice. And so this would give me an idea. I could look at this and say, oh, about 50 of my students ought to be fit this criteria, and that would be a good answer. Okay, an example. A machine produces ball bearings which are to be used in a particular machine. Okay. In order to be usable, the bearings must be between 0.248 centimeters and 0.252 centimeters. So these are chosen, they're right around 0.25. Now, it is in the nature of the manufacturing process that these bearings are not going to all be exactly the same size. There is always going to be some variation. However, it has been determined that their radius, okay, which is what this is doing, probably diameter would have been a better measure, but we've set on radius, is on the average 0.25 with a standard deviation of 0.001. If we do 1,000 of these, okay, how many of them will be usable? Well, okay, so what the usable ones are the probability between 0.248 and 0.252. Again, so that we can calculate, we take the z-score of everything. Right, this is what we're doing. Mean, standard deviation, mean, standard deviation. I've left it in terms of variables in the middle because my x is a variable. Anyway, I do my calculation, and it's asking what's the probability that z will be between 2 and -2. I do the calculation on this. It's a table lookup, and looking up the same number both times, add them together, and be 95.44%, 0.9544 of my 1,000, okay, are going to be usable. So I take this fraction of my 1,000, and so I get an estimate here of 954.4, and we round it off to 954. Okay, example 2. The Green and Gooey Fertilizer Company sells a product it collects from feedlots in 50-gallon barrels. Okay, you call them 50-gallon barrels, but they're generous. Each barrel contains a mean of 50.1 gallons, and so if you're trying to always have at least 50 gallons in something, because of the variation, you're always going to have to put a little bit more in. Okay, and so what we're doing here, we're saying, okay, saying it's normally distributed with a mean of 50.1, but we're going to play around with what the standard deviation is. Okay, we'll do if the standard deviation is 0.05, we'll ask, okay, what proportion of the barrels are going to be under 50 gallon. Okay. If it is 0.03, what proportion is under 50 gallon? Okay. And we do the calculation first with 0.05. Again, x less than 50, do the z-score. Okay, this is saying, okay, z is less than -2. It's a thin tail. I do my calculation, and so this happens like 0.0228, so a little over, more than 2% of the time. Okay, if I do it 0.03, so I've just made the standard deviation just a little smaller. What has happened? Well, I do the z-score, and I get this number. When I take the z-score, it's not on the table. It's too big for the table. And in this particular case, what I did, I put in the largest number on the table. Okay. Other cases, and you can see by putting in the biggest number on the table, I got like 1 in 1,000, 1/1000th probability, or 0.1% of the time, a very small probability. So for practical purposes, I could, when I go off the table, I could just put in a 5 there, because it's just almost 0 probability. Example 3. A candy extruder that is properly calibrated will make candy that weighs, on the average, 2.3 ounces with a standard deviation of 0.1 ounce. Let x denote the weight of the piece of candy, and what is the probability that x minus 2.3 is greater than 0.3? What is the probability that x minus 2.3 is greater than, absolute value is greater than 3? Do these calculations. Okay. Well, this first one, and again, this 2.3 is not chosen at random. It's chosen so that I can divide both sides by the standard deviation and have a z-score here. Okay. And so I get that z is greater than 3. I do the table lookup at 3, and so the probability of this happening is 0.0013%. Now, I wanted to contrast this. What's the difference when we put an absolute value around this? Okay, go through much the same procedure. Again, we've chosen this right here because we wanted to be able to divide and get a z-score. Okay, so we divide, we get a z-score. Okay, and this is absolute, and the absolute value around it. Now, how do you handle it when you have an absolute value around it? When the absolute value is greater than 3, that means that either z is greater than 3 or z is less than -3. So we either have it over here or over here, and we calculate we have twice. We calculate the probability of the tail and multiply it by 2, because there's twice as much chance, because you could either be too big or too small in this particular case.